And this builds upon our previous experience. So let me just recap a little bit what happened last time. It was we did this x squared y double prime plus xy prime plus x squared minus 4y equals to 0. And we were looking for solutions of the form that looked like y equals to summation of n equals to 0 to infinity of an x to the n. In other words, we were looking for some power series solutions. Okay? And when we look for these power series solutions, the outcome was that a lot of these, the first two were forced to be 0, and all the odd ones ended up being 0. And we had something like, there was like a2 x2, but then x cubed wasn't there, and there was something times a2 x to the 4th, and so on and so on. Okay, so that's what happened. Now, Frobenius method tries to hunt for more solution of the same thing, because right now this is somewhat incomplete, because this is the second order. How many linearly independent solutions should you be getting? Second order, you should be getting two linearly independent solutions. But see, there's only one free parameter, so you only found one parameter of solutions. You need two free parameters of solutions. So this is not complete. So that's why this other approach is done. And so this was what we were doing. This is what we call the power series method. And it's actually, it could fail when you have y double prime vanishing for x equal to 0. If something like that happens, then it could fail. So that's why power series is not perfect. So instead, Frobenius says, try x to the r times summation of n equals to 0 through infinity of an x n. So that, for example, this solution can be written like this. This is x squared times a2 plus something a2. So if I just treat this as 1, it's like, let's just treat something like 1 here. So it's like 1 plus something else, x squared, something like that. So because the very first non-zero term is x squared, in this case, you're going to be getting r as 2, and it'll start from 0, but a0 won't be 0. So Frobenius is saying that we want to look for a solution that's like this, with a0 being the first non-zero term. You see what I'm saying? You're looking for a solution of this form, such that the very first coefficient that appears is non-zero. That's the important part, okay? So that here, like x squared is the first thing that's non-zero, so that will be your r. Is that all good? Okay. And therefore, if I move this inside, just like how we did last time, when you move this inside by distributive property, x to the n times x to the r, that's x to the n plus r, right? So the way we are approaching this is you set y equals to summation of n equals to 0 to infinity of an x to the n plus r. That's your solution. Okay, so with this, what are we planning to do today? Well, I'm going to be very ambitious today, and I want to solve the Bessel equation for any n. So, Bessel equation for order n is x squared y double prime plus xy prime plus x squared minus n squared y equals to 0. And I want to look for the solution of this Bessel equation in the Frobenius type. So let's try that. Okay, solution. Well, we have our y. Let's find the y prime. And as we did last time, it's nothing different. You just differentiate. So if you differentiate x to the n plus r, that will be an n plus r x to the n plus r minus 1. Y double prime would be summation n equals to 0 to infinity an n plus r minus 1 x to the n plus r minus 2. And then we just plug these into the Bessel equation and see what we get. Right? So when x squared is multiplied to this one, it's going to be summation of n equals to 0 to infinity of an n plus r minus 1. Oh, I need to back up a little bit. I'll put this as m, okay? Because I'm already using n for something else. I can't use the same thing, so that's going to be m, okay? So you have n plus r minus 1, x to the n plus r. The negative 2 went away because you multiply by x squared. Is that good? Mm-hmm. Okay. And then the next one, xy, would be this times x, so that negative 1 will also disappear. And then you want to distribute these two. So we'll have x squared multiplied to this, and negative m squared multiplied this. So we're going to have two terms. The first term would be summation n equals to 0 to infinity of an x to the n plus r plus what? Plus 2, right? 2, because of x squared being multiplied to y. And then plus sigma n from 0 to infinity, and there's a negative m squared multiplied to an x to the n plus r. And that has to equal to 0. Okay?
So where's the plus 2 from? Where's the plus 2 from?
Where's the plus 2 from? Well, we have x squared times y, right?
Okay.
X squared times y, and y is this thing. So if you multiply by x squared, then x squared and x to the n plus r, they have the same base, so that the exponents add up. That's how you get n plus r plus 2. All right, let's continue. Now, looking at this, which one of these need to be shifted?
The third term?
The third term. This has to be shifted, right?
Yes.
Why?
Because there's a plus 2 there.
Yeah, everyone else has x to the n plus r, but this has plus 2. So that's different. So that's the one that we should shift. Okay. How do we shift?
So what we can do is we need to change the n. So like in order for that exponent to become n plus r, and it looks like we could change n into n plus n minus 2.
Yes. You can replace n by n minus 2. So here's the shifting. This right, shifting. Shifting is done to third term by the following. We have summation of n equals to 0 to infinity of an x to the n plus r plus 2. And for any of the n that you see, all the n is replaced by n minus 2. So all the n is replaced by n minus 2. Okay, so that when these two cancel, you get n plus r, just like the other ones, right? But then this one is n equals to 2. If you solve for n, it's n equals to 2. And now if you go back and see what's happening is that now they have all x to the n plus r as we wanted. However, there's another discrepancy, which is that other ones all start from 0, whereas this one starts from 2. So now what do? No, you expand it. Yeah, you write out the terms, and you write out the first 0 and 1. You split out those terms so that the summation starts from 2. Write down the first 2, and you write the rest. Okay? So let's do that. Okay? Let's do that. So this very first one, when n is 0, you get a0, 0 plus r, 0 plus r minus 1, x of 0 plus r. That's what you get when you plug in 0 to this first one, right? And then you have a1, 1 plus r, 1 plus r minus 1, x to the 1 plus r. And then because we've split off the first two terms, we can now happily write from n equals to 2 to infinity and write the same thing again. So that's n plus r minus 1, x to the n plus r. That's it. Okay, now the next one. Let's work on this one. That has a0, 0 plus r. So I put, when n is 0, I get a0, 0 plus r, x to the 0 plus r. And the next term is a1, 1 plus r, x to the 1 plus r. And then I can write down summation of n equals to 2 to infinity of an, n plus r, x to the n plus r. Okay, then here we have the shifted one, not this one, but we're going to use this one, which starts from 2 anyways, right? And then it's an minus 2, x to the n plus r. Okay. And then, what else? It's this one, and then the next one is this one here. It's negative m squared a0 x to the 0 plus r plus negative m squared a1 x to the 0 plus r, 1 plus r, sorry, 1 plus r. And then we have summation from 2 to infinity of negative m squared an x to the n plus n equal to 0. Okay, so now all the sigmas have the same starting number, and they all have the same x to the n plus r, so we can happily gather them in a single sigma.
I have a quick question
Yes.
about that. What if you're working with n minus 2? Like, how does that work?
What if we work with n minus 2 where?
Like, you know, like under that sigma, like it's n equals 2 this time, but what if we're working with n equals negative 2?
I see. Okay, so the question is, what if some of the terms start with 0, but then you have n equals to -2. What do you do? How do you make them equal? That's a really nice question, right? What would you do?
The same thing but backwards.
So let's say Fn here and Gn here. How do you make them start at the same place? This would be what? F of -2 plus f of -1 plus summation of n from 0 to infinity of Fn, right? So they both start from 0. Yeah. So whatever that's lower, that's the one that you split out. Okay. I haven't thought about that, yeah, but that's great. Okay, so we do that, and let's see. Let's collect the ones that have x to the 0 plus r. So here's 1, here's 1, here's 1, and that's it, right? X to the 0 plus r. So, and all of them happens to have a0 in there. So I'm going to factor that out as well. So if I factor out the a0 out, the very first one is r times r minus 1. Right? It's a0 times r minus 1. And there's another r there, so plus r. And then there's a minus m squared. And you have x to the r. Plus, now let's look for the ones that have x to the 1 plus r. So there's one here, there's one here, and there's also one here, okay? And again, these also have a1s as a common factor, so let's factor that out as well. So if I factor out the a1, you have, what is that? That's 1 plus r, and then r, and then 1 plus r as well, and then minus m squared, x to the 1 plus r. Okay. And then we have a humongous sum. So summation plus, you have n equals to 2 to infinity, a very big sum. And, well, it's everything that's remaining, but let's first collect the ones that have a_n's in there. So I have this one, this one, this one are the sums with a_n's in there. So I'm going to factor the, so it's going to be a big one. A_n will be n plus r minus 1 there. It's from here, right? And then the next one is here, n plus r, that one, plus n plus r. And then the last one here, this one has minus m squared. And these are the ones with an, but then there's another one with an minus 2. It's this one, right? So there's an minus 2 times x to the n plus r has to equal to 0. Check if I have made any mistakes, because if I make a mistake along the way, then it's going to be very wrong at the end of the day. So make sure that you're not making a mistake. Hopefully not. Do you have any questions about any of the things I wrote? Okay, there are more than 10 people looking at this moment, so if nobody's finding any mistake, I guess I can trust you guys, right? Okay. Now let's just erase everything. Continue. Okay, so that means we have several things that are 0. I'll just say it. So I know that A0 r squared minus r plus r is just r squared, so r squared minus m squared has to be 0. And then a1, that's r squared plus r, 1 plus r, so that's what's that, r squared plus 2r plus 1 minus m squared equals 0. And this one, that's rather huge, but I think I know what it is. It's an. So if you multiply this out, you get n squared, nr, negative n, nr, r squared, negative r, and then you have n and r. And yeah, if you expand everything and simplify, you're going to get n squared plus 2nr plus r squared minus m squared in here, okay? And then plus an minus 2 would be 0. Okay? All right. So this is not that complicated compared to what we were doing yesterday. It's almost at the same level of difficulty. I'm not saying this is easy, but it's like on par with what we were doing yesterday. Well, it's slightly harder because we were just doing it for 2 squared yesterday, or Monday. But now, today we are actually doing it for general n. Okay, but here's a really important thing that we want. Look at this thing. Now, if we have two things multiplied and it's equal to 0, it's either a0 equal to 0 or r squared minus m squared equal to 0, right? It's one or the two, one or the other. However, one of them is invalid. We don't want it. Why?
Trivial.
Okay, that's okay. That trivial means for PDEs. Okay, that's for PDEs. Here, our assumption is that when we first started with so Frobenius was that y is equal to summation of an x to the n plus r, n from 0 to infinity, and a0 cannot be 0. That was our assumption, right? So that because of that assumption, we can't have this. Okay? So immediately, you get r equals to plus or minus m. R equals to plus or minus n. Because if you solve this by moving the m squared to the other side and taking the square root, you get r equals to plus minus n. And this one here, this is what's called the initial equation. And there's actually a separate formula for it. So if you watch videos on Frobenius method, in many cases, before doing the computation, they'll start by solving the initial equation. There's a formula for writing it. You write it right away and then solve that, and then you start with the known value of r. That makes it slightly easier. Okay? But here, we're not going to be doing this for many cases. We're just going to be working with the Bessel function, so I'm not too interested in explaining what the formula is. Okay, so anyways, we got r equals to plus minus n. Now, in general, when you solve a Frobenius method, this doesn't have to be an integer. In fact, when we had our original Bessel's differential equation, which was x squared y double prime plus xy prime plus x squared minus m squared, y equals to 0. We could very well write down this number so that it's not a square of an integer. It could be any number alpha, and you could still do this without any problem. In that case, the answer would be plus or minus alpha, right? Which is not an integer. And guess what? You can still solve that as well, right? And of course, for PDEs, we will mainly be concerned with two types where this is an integer, alpha is an integer, just like what we were doing here, or when alpha is a half integer. Okay? Those happen to appear for solutions of PDEs later. That's why we are doing it here. Now, if the two numbers that you get out of solving the initial equation, by the way, initial equation will always be a quadratic equation, so you're always going to find two solutions. If the two solutions differ by a non-integer, then each one of these will give you a solution in the Frobenius type. Okay, that'll be nice. However, if you have two solutions where they differ by an integer and you start with the lower one, then you start with the lower number and you start doing the sigma thing, going up by integers, and you arrive at the other one, something happens. And two things could happen. One is that when it meets, it might somehow create the other one as well. So you start with the negative number when the two solutions of the initial equation gives you two numbers that are differing by an integer. You start from the lower one, you start going up by integers. When it meets, it might be able to somehow give you a nice consistent equation so that it generates the other answer as well. So you can get the two solutions at once. Or, that's the good case. Or it could be a bad case where you start from negative and you get up to that point. Suddenly, they contradict each other and everything before that becomes 0. And you just start with non-zero ones starting from the other one. So you start with the top one. So in that case, you just get one solution of this form. Now, if that happens, if the bad case happens, what happens is that the other solution is not of this form, but you have to add some logarithmic function. So you have to plus log of something. And that's very complicated. Okay. Now, if this is an integer or a half integer, you do see that this would differ by, these two numbers will differ by an integer, right? If you have positive 1/2 and negative 1/2, they will differ by 1, which is an integer, right? Or if this is an integer, then of course the difference will be an integer. Okay? So unfortunately, for the physically interesting case, we will always have this problem of the two solutions of the initial equation being differing by an integer. Okay? And naturally, the next question is, okay, then which case is it? Is it the bad case where we get the logarithmic singularity, or is it the good case where you just start from the lower one and everything works fine? Okay? And the answer is it's the bad case. Oh no, right? It's pretty bad. Okay. So what you do is you just work with the top one, but then you would find the other one using that logarithmic trick. But you know, it's extremely hard. I have one done explicitly for when m is equal to 1. I find the positive one and the other one by using the logarithmic one. It's very long. I don't think you really want to watch that video. It's just not worth your time. Okay, so please don't watch that video. Okay. Instead, what we can do is we can kind of come up with the formula for the other one using the ones that can be written when these are not differing by integers. So I'll explain how that happens later. But my point of explaining that is that when you have two initial solutions and they differ by an integer, you always have a solution if you take the higher number. Okay, so maybe I should write that down here. Frobenius method always gives one solution, gives a solution corresponding to higher R, higher R value. So that's what we are going to do. All right. Okay. So we take R to be, that means we are going to take R to be M, and let's rewrite all these using R equals M. So we have A0 times M squared minus M squared equals to 0, which doesn't say anything. It just says 0 equals to 0. So A0 is free to be anything. Okay. So A0 can be anything, any number. Now if you plug in R equals to M here, you get M squared plus 2M plus 1 minus M squared equal to 0, which gives you that A1 2M plus 1 equal to 0. Okay? And in this case, because we're working with M integers, this is never 0, so you end up with A1 being 0. And for this one here, an n squared plus 2nm plus m squared minus m squared is what you have, plus an minus 2 equals to 0. So that if you solve for an minus 2, this is negative an m squared plus 2mn. Right?
Shouldn't it be n squared, not m squared?
Oh, sorry. N squared. Oh, thank you so much. Okay, yeah. It could have been a disaster if that happened. Okay. All right. So you have that. And then we want to solve this for higher numbers. So an is equal to negative 1 over. And let's factor this. This will be n times n plus 2m. Okay. Of an minus 2, where n is 2 or greater. Now we are assuming that m is a positive integer, right? So the denominator will never be 0. That's good. That's you should check that. Okay. And this means that since a1 is, if a1 is 0, then a3 would be something times a0. So you get 0. Okay. So immediately you see that all the odd ones will be 0. Okay. A odd will be 0 because of what we have. But let's start by thinking about what A2, A4, AN, and so on will look like. Okay. So let's see. So we're going to have A4. No, not A4. Sorry. A2 is negative 1 over, it's 2 times 2 plus 2m of A0. So this is negative 1 over 1 times 1 plus m times A0 over 2 squared. Okay. Now, I don't want to write 4 because I know that what the answer should be. So if you write in this form, it's going to follow some pattern. Okay? All right. So then what is A4? A4 would be negative 1 over 4 times 4 plus 2m times A2. And this would be negative of negative, so it would be positive. And again, there's a 2, another 2 can be factored out, so it's 2 times 2 plus m. And then A0 over 2 to the 4th power of 1 times 1 plus m. So see what happened? I factored the 2 out, another 2 out. So it's 2 times 2 plus m, and it's 2 to the 4th power because there was a 2 squared and another 2 squared is there. Okay? And then once you look at this, you kind of see some pattern emerging already. So because of this negative, negatives will alternate, right? Negatives will keep alternating. And if you do A6, it will be negative of 1 over 6 times 6 plus 2m, A4. So this time it'll be negative 1, negative. And then again, if you factor this, the 2 out, so another 2 squared comes out. It'll be 3 times 3 plus 2m, 2 times 2 plus m, sorry, 3 plus m, sorry, 2 plus m, and then 1 times 1 plus m, and then A0 over 2 to the 6th power. Okay. Now, do you see that for A2k, it'll be negative 1 to the kth power, right? Because when k is 1, it's negative, k is 2, it's positive, k is, see, k is 3 will give you 3 times 2 is 6, right? And it's indeed negative, right? And then, so this one corresponds to k equals to 3, right? Look where you get the 3. You get 3, 2, and 1, right? What's that called? Factorial, right? That's factorial, so that's k factorial. And then you also have 3 plus m, 2 plus m, 1 plus m. Sounds really familiar. It's really similar to the factorial, except that if you want to make this as a factorial, you better multiply top and bottom by m factorial and m factorial. Then this will be m times m minus 1 all the way up to 1, so that this will become 3 plus m factorial, right? So what I'm trying to say is that if you put an m factorial, m is what? M is m. So if you put m factorial here, then you end up with k plus m factorial. Is that good? Right? And then 6 corresponds with 6, 4, 4, 2, 2, right? So it's always A0 over 2 to this number, the same number as this one, so it's 2k. That's quite nice. That means we actually solved it for everything. Okay? Yeah. Now, if you want this to be really rigorous, you would actually want to prove it by mathematical induction. You can do that, right? But there's no real need for that. I mean, we're just here to not prove things, but to do calculations. So you should be pretty convinced that this is indeed the case, right? Okay, so now let's write down what the solution is. So the actual solution is, so remember we have y equals to summation n equals to 0 to infinity of an x to the n plus r, but right now r is m, right? So that's what we have. And it turns out that for odd n, it disappears. So odd n, it disappears. And when you have n is equal to 2k, that was the language we're using, right? When n is 2k, then this is non-zero, right? So the very first one would be k equals to 0 until infinity, and we have a2k there, because odd indices are 0. Okay. And then because now we have a2k, we can rewrite that in this fancy sum as negative 1 to the kth power m factorial over k factorial k plus m factorial, and then a0 over 2 to the 2k, and then x to the 2k plus n. Oh, sorry, this should be 2k. N is 2k, so I should have replaced n by 2k. Okay? So that's what we have. All right? And then because we can take a0 to be anything, we could take a0 as 1, but then the standard one that we choose would be we take a0 as 1 over m factorial. If you take a0 as 1 over m factorial, that nicely cancels this. Right? See, m is a constant. It's fixed for each m. Well, for each m, this m factorial will be fixed. So if I plug that in, we have this solution which is called Bessel function. Use j. I actually don't know why j is used, but j is used. And jm of x is defined as a summation of k equals to 0 to infinity of negative 1 to the kth power over k factorial k plus m factorial, and then as you can see here, just a minute. Yeah, sorry, there is an additional one where you multiply 2 to the m top and 2 to the m down here, so that you want this to be 1. So you actually need 2 to the m as here as well. Okay, sorry about that. So and that results in having this one having the same power, 2k plus n. So you end up with x over 2k plus n. So that's clean as possible. Right? So that's called the Bessel function of order n. Okay. Is this okay?
Will we have something like this on the exam, or will we
Not tomorrow, though tomorrow's one is not this one, but I'll have to think about this. It'll be at some point too much. But I might do something that's slightly easier. I'll have to think about it. Okay. Now, what would happen if m was not an integer? Well, everything that we did would carry over. The only problem is you're going to be having something that starts with k plus some non-integer alpha, right? And it goes down like a factorial, right? But we don't have any name for that. So there was a need for extending factorial beyond integers. So here's a brief title: How to define factorial for non-integers. How to define factorial for non-integers. And if we define it, then you can even write this formula for non-integers and it will still be true. Okay. So the way we start is we start with the fact that the Laplace transform of t to the n is equal to n factorial over s to the n plus 1. Now if you know this, wonderful. Even if you don't know this, it's okay. I'll write down what it means. The Laplace transform is integral from 0 to infinity of t to the n. You take the function and you multiply it by e to the negative st, and you integrate by t. And that gives you n factorial over Sn plus 1. Okay? Now, if you're a mathematician looking at this, it would intrigue you a lot because, hey, here you have an integral formula which produces the factorial. So the natural question that you would have is that, oh, is there a way to use this left side as a different definition for n factorial so that you can just, you're able to define this for something that's not an integer? A natural question to ask, right? So here's what you do. First, you plug in s into something. What would you do? S equal to what? To get the n factorial only, what should you do? S equal to? 1. If you take s to 1, what do you get? You get 0 to infinity of Tn e to the negative t dt equals to n factorial. Okay? So we have this nice formula. The next question is, well, does this left side make sense for something that's not an integer? And the answer is yes. So for example, if you put 1/2, think about what's going to happen. You have a square root of t, some function, right? This is a rapidly decaying function, right? So if you multiply them, you're going to have over, the graph will be like, it's going to start with some value. Well, it'll start from 0. But it's going to go up and then rapidly decay down to 0. Would you believe that this would have a finite number? You would, right? You would believe that this has a finite number. Indeed, it does. So for any positive n, even if it's not an integer, you can definitely do this integral. Because exponential functions decay to 0 much faster than any polynomial, this will always be able to be calculated for non-integers. Yeah. So that's a good definition. And Gauss looked at this and said, okay, we're going to define this as pi of n, or just any x, pi of x. Oh, I can't, yeah, pi of x is equal to 0 to infinity of t to the x e to the negative t dt. Now, there's sometimes because math builds on previous knowledge and it carries on, sometimes along the way somebody does a bad definition and it gets stuck and it's too late to change. So when Gauss came up with this, actually somebody else already had this in the books, except that their definition was slightly different. It's called a gamma function. The gamma function of this is called gamma of x plus 1. It's rather strange why they did that. So the definition of a gamma function is equal to, I forgot the name of this mathematician who made this change. I mean, who started with the wrong definition. Too bad, but you can look it up, okay? So somebody started with this definition of gamma function. So if you're curious, just search up why is gamma function shifted by 1. Okay? It's quite bad because according to this definition, what we have is that gamma of n plus 1 is n factorial. Okay? So if you want to convert n factorial into gamma function, you have to add 1, unfortunately, under this definition. Okay? Yeah, but what can we do, right? Okay, so using this gamma function because it's a standard. Of course, I wish people start using the pi function more because it makes sense more, right? And it has a simpler formula even. But assuming that it doesn't change soon, you're going to be stuck with the gamma function for a while. I don't think it's going to change in my lifetime. So here's the definition of the Bessel function. The Bessel function is j of alpha equals the summation of j of alpha of x. Right? J of alpha of x equals to k equals to 0 to infinity of -1 to the kth power of k factorial k plus, oh, not k plus m, but it's not m, we have alpha, right? So we put gamma function of k plus alpha, but because of this ridiculous definition, you have to put +1 there. And then you have x over 2, 2k plus m. So that's your gamma function. Now, I told you about this other function that can be obtained by starting with the negative alpha, right? So what happens is that this actually works for negative alpha. So let me say that. So this is called Bessel function of first kind. And then
is the x divided by 2, should be 2k to the m or 2k to the alpha? Like,
oh, thank you. This should be alpha. Thank you. We're not using m anymore. It's alpha. Yeah. All right. So that's j alpha, and then so if alpha is not an integer or integer plus a half. If it's not of these cases, actually, I see. It's actually the integers that cause the problem. Even if for integer plus 1/2, it runs with the problem that the two initial solutions are differing by an integer. This doesn't suffer from logarithmic singularity, so it's not going to be a problem. Sorry. So if alpha is not integer, so then the Bessel equation has general solution. Y equals to C1 times J alpha x plus C2 times J negative alpha of x. So this formula with negative alpha will do its job, no problem. It's not going to cause any trouble. Now it's the case when it's an integer that's going to cause a problem, and the way we do this is by defining if alpha is an integer, then we define the Bessel function of second kind. And people usually use y. I don't know why they chose these letters, but it's like this: y of alpha of y, x, is defined as nu going to alpha of j alpha of x cosine nu pi x. Is that right? Nu pi. There shouldn't be any x. Sorry, so there's nu pi. Okay. minus j minus alpha of x over sine of nu pi. So, and although you can find this other solution by doing this logarithmic singularity thing, it's a lot harder. Now, you kind of see that because j minus alpha and j alpha are the solutions when it's not an integer, this thing on the top will definitely be a solution to the Bessel function, right? Yeah. And for each fixed nu, these are just constants, so you're really just taking linear combination of the two solutions that's already there. Okay? And if you take this limit, what happens is that when nu is an integer, cosine nu pi is close to 1, whereas this will get close to 0, right? So you can't evaluate it at an integer. However, you can still take the limit because the top one will become 0, okay? And but because it's still a linear combination in other cases, you can kind of have an expectation that this will still satisfy the Bessel equation, right? And then mathematicians worked out that in this case, the solution C1 j alpha x plus C2 of y alpha x will be a solution in general. Okay? So that's what Bessel function of second kind is. Now the Bessel function of first kind will look like the following. It's going to when alpha is positive, it will start from 0 because the first few times will be 0, and then it's going to go up, and then it's going to go like that. On the other hand, actually it doesn't decay to 0. It just becomes more like a fixed amplitude sine curve or cosine curve. And then the y, on the other hand, has a logarithmic singularity down here. So it'll be something like this. And then there's some theorem where if it's in the same order, then their zeros should be alternating. So that's another property. Okay. All right, sine pi dot special report gamma. Okay. So I want to show you the graph of the gamma, the Bessel function that we just made. So define Bessel, and it will be a function of x, but also order m. Okay. So that's how we're going to say it. And then we're going to say the very first term. So S will be the summation. The very first term is, let me think. It's negative 1 to the 0th power, so it's 1 over gamma of, very first one is 0. Oh, so that's just 1. And the second one is 0 plus n plus 1. And then you do this, and then you multiply by, let's see, x divided by 2 to the power of 2k plus m, right? And k is 0, so m must be n. Okay. Okay, so that's the very first one, and then we're going to do a for loop to add up everything. So for I in k in range, let's start from 1 until, we can't do infinity, let's just do 50 and see. If it works, it works, and it's good. If not, we'll have to work on something, okay? So there's 50 terms, and then it's s plus equals to, first it's negative 1 to the kth power, and then you multiply by x over 2 to the power of power of 2k plus m, right? 2 times k plus m, that's what you need. And you divide it by, instead of the factorial, unfortunately Python doesn't have factorial on its own, and let me just use the gamma function. Gamma of k plus 1 is same as k factorial, so I'm going to use gamma of k plus 1 times gamma of k plus m plus 1. So you do that, then that's it, and then we return s. Okay, so that's going to be my Bessel function. Now let's try to draw the Bessel function from x equals to the linear space, and let's draw something like 10 times 0 to 10, 0 to 20 maybe, 0 to 20, and we'll divide this into maybe 101 points. And then after this, let's plot x comma Bessel of x comma 1. Okay, so other than the gamma function, we're actually doing everything from the scratch. This formula right here, we actually got it by hand calculation. Okay, so we're not like trying to look at the books. It's really the thing that we found out, and we want to know what it is just by drawing the graph. And no, that's not the graph. Something's not right. Can't be that one. Oh, I should have put k here. Sorry. So that's k. And then let's draw that. Okay, good. That's the one. Okay. All right. So you see that it starts from 0 and it goes like that, and eventually it gets closer and closer to some sine function or cosine function. That's what happens. We can draw other orders as well. Let's combine x comma Bessel x2. See what happens. So you have this other function, and that one also does that. Okay. Now we will be, as I explained in the very first class, that very first Bessel function introduction on Monday, that this function comes out when you try to solve the wave equation on a circular drum, right? So imagine that you're taking a drum and you're beating the drum, right? And then when you beat the drum, it's going to vibrate. Okay? And this one will be actually the radial direction function. So if you have a drum that's beating and you have these things vibrating, then what do you think it's going to look like? It's going to do this, right? Yeah. Like that. So that looks pretty similar. Another place that you can see Bessel function is that next time you go to a pond, or some place that's like still waters, and you throw a stone on the pond, then what do you get? You get water ripples, right? That's circular. Okay? If something's circular, and if you take the cross section of that, then that cross section bump, the wave function of the cross section will look like a Bessel function. This is a little bit different from like water waves in the sea, that they go like parallelly, right? That's not going to be a Bessel function, but if you drop a stone in the pond and it has circular patterns, then starting from the center of the circle and you go radially, that's going to be the Bessel function, okay? With some order. Okay? So hopefully that kind of gave you a better idea. Oh, by the way, I think this is also a good time to show you the graph of the gamma function. So what's x equals to in space, say 0 to 4. And divide by 101 points, and then let's plot x comma gamma of x. And that's the graph, and it actually has a singularity of 0, so let's try to draw it slightly after 0. So let's say start from 1. So we plot it from 1. And it's going to grow like the... So you remember that gamma of 1 is actually 0 factorial, which is 1. Gamma of 2 is 1 factorial, which is 1. So it starts from 1, it dips slightly, and then goes back up again, and goes up. Okay. In fact, if you start from, say, 0.2, then this is like the graph of the gamma function. Okay. What else? Oh, since we're up to that, let's think about the heat kernel. What was the heat kernel? Can somebody help me? What was the heat kernel? Define k of xt as a return, what was it? 1 divided by square root of 4k,
4 pi kt.
4 times pi times k times t. And then you multiply that by exponential function of what? Negative
X minus y squared.
X minus
Like x.
y squared. Okay, so we'll just choose the x squared because then we can just see it. Oh, but isn't there over 4t?
Over 4 kt.
Over 4 kt, right? Over 4 kt. 4 times k times t. And oh, you know what? Let's just make k as 1 because we just want to look at the value, right? So this is that. Should be good. Okay, good. So define that, and then we're going to plot it for x comma. Oh, now we have to define x again. X as Lin space from negative 3 to 3 of with 101 points, and let's plot x comma k of x comma 0.1. Let's just put 1. Let's see what happens first. Okay, so that's a nice looking Gaussian function, right? But here's what we want to do. We want to compare it between different times. So let's do comma. What happens at 0.5, and then what happens at 1, and then what happens at 1.5. So let's draw 3 things. And what happened is that gradually it spreads out. Right? So the heat kernel, this is at 0.5, and the top goes down and down, right? Now, what if you did for smaller values of k, smaller values of t? Then the peak will just go rise up, 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 and then it's going to produce an infinity, right? So if you start from 5 and 0.1 and then 0.01, if you draw this is what's going to happen, right? So as you send time t to 0, it peaks, and if you do the integral from negative to infinity, you'll see that the value of this integral is always 1. So the area is preserved, but the peak is going up, and that's a recipe for developing a delta function. Okay, so such a function will give you a delta function, which if you convolute the delta function with another function, it samples the function at a point. Okay. So that's what it does. All right, so I'm thankful that this did work. Now I need to figure out how to turn this thing off. Okay. All right, now we are going to just make sure logged out. Okay, now we are going to work with the wave equation as I promised. Wave equation, wave PDE on a disk. So it's a circular drum. Right, so as discussed, you have UTT equals to some c squared Laplacian of u. That's the wave equation. And if you write this out, UTT would equal to, oh, but before that, let me just write down this other conditions, okay? So we're going to think of u of capital, I don't want to use capital R. Let's use A. So let's say you have a drum whose radius is A. Okay. So UA theta t would be fixed to 0 for theta between negative pi to pi, and t for all times. And then there's this condition about periodic in the theta direction. So u r pi t should equal to u r negative pi t, and also u differentiating in the direction of theta r pi t should equal to u r negative pi t. And then there should be some initial condition u of r theta comma 0 as some initial condition. We're going to call it fr theta. And there will be another initial condition for the time t derivative. Because it's a second order differential equation for t, you have to provide not only the initial value of the function, but also the initial derivative of the function. So that should be given as well. And if you recall, this is nothing different from the D'Alembert solution we had before, right? So in the D'Alembert case, we had u and ut given as f and g, and on the real line we were able to solve it that way, right? Okay, so this is the equation that we are going to solve. Well, I'll say solve with quotation because the reason I don't want to put explicit values here is because I don't want to actually solve it for specific ones, because you end up with an integral that you can't actually solve. You can only numerically solve it, but still it will give you something. All right, so let's try to do it by first writing down u, Laplacian of u in polar coordinates. So it's u t equals to c squared times u r r plus 1 over r u r plus 1 over r squared u theta theta. And then we start with the step 1. What's step 1?
The separation of
Separation of variables. You separate the function as products of simpler functions. So we look for non-trivial solutions of the form u r theta t as capital R of R, theta of theta, and then t of t. So for everything that everything that looks like that, and then hopefully we get enough building blocks of the solutions so that we add them up, we get the general solution. That's our idea. So what's going to happen is that this thing, when you plug it in, you'll still be able to use that argument that if you divide by something, one side is a function of something only and the other only, so it has to be a constant. You can do it that way. The only problem is that because we have 3 separate variables, we have to do separation of variables. We have to assign constants twice, and you're going to have 2 constants. So I'll show you. Okay. So if I plug this on the left side, I get R of R, theta of theta, t double prime of t equal to c squared times R double prime of R, theta, theta, t of t. This is just by plugging in here. You're differentiating twice by R, so only R gets differentiated. Right? And then plus 1 over R. R gets differentiated once. Theta of theta, t of t, plus 1 over R squared. And then you have U, not U, sorry. R. Theta is differentiated twice. And then you have t of t. Okay. And then what we're going to do is we're going to divide everything by r theta t.
I have a question.
Yes?
We can't divide the c squared.
If you, yeah, actually, let's do that as well. Thank you.
Thanks.
Let's divide by c squared as well, like that. Okay, so once you do that, then they go away. Oh, let's use red. So these go away. This cancels. The t's cancel. C squared cancels, thank you. But the other ones, it's kind of...
The theta doesn't cancel there?
Well, okay, so this theta cancels with this one, but there's a theta double prime, which this one doesn't cancel with this one. So you can only cancel stuff if you split them, if you expand the fractions. Okay? If you make it as like this over this, plus this over this, plus this over this, then you can do it. Okay? But already we can make some arguments here. You see that the left side is independent of r and theta, right? Whereas this side is independent of t. All the t variables are gone. Right? So if you set this equal to a function of, so initially you think of this as some function of r, theta, and t, because those are what you see. You look at this and say, hey, this function doesn't depend on r and theta, so these don't matter. Right? But then you look at here and say, oh, over here, it doesn't depend on t, so t doesn't matter at all. So what's a function that doesn't change when you change its variables? A constant function. Right? So that's the argument. So we can write this as equal to negative lambda. Okay? Just a minute. Is that what we want? Let's see. T squared lambda. Right. So we have this. It's certainly over there. Okay. Sine, cosine. Okay. Yeah. Alright, so I like that. Okay, so I want this to be negative lambda. Okay, so that's going to split this into two things. One will be on this side, it will be t double prime equals to negative lambda of t. Negative lambda c squared t. On on the other side, what you have is you get negative lambda r. You know what? Let's see. Let's not do it this way. Let's not do it this way. We'll we'll now split. Okay, so let's do this over this, and theta theta cancel. So you have r double prime over r of r, right? And then you have this over this, theta theta cancel. So you have plus r prime of r over r of r, but there's an r here. Okay, and then you have this over this. So r this time cancels, and you have plus 1 over r squared of theta double prime over theta. Okay? Now, so again, the argument that we want to make is so that one side is a function of r only and the other side is a function of theta only. And I like the fact that these only have r's in there, but I don't like the fact that this one has r squared in the denominator. So what should we do? Yeah, you multiply by r squared to get rid of it, right? So we get negative lambda r squared equals to r double prime of r over, sorry, that should have r squared there. So r squared r double prime of r over r of r. And we're going to move everything to the left side. So the ones that have r's, we're going to move it to the other side. So I'm going to move it here. This one should also move to the other side, but we multiply by r squared, so r squared over r becomes just r on top. Equals to, now you have theta double prime of theta over theta of theta. Okay. And now we can make that argument. You only have a function of r on the left side, and you have a function of theta on the right side. Okay. And then we say this is equal to negative mu. Okay, so again, it may have to be equal to a constant, right? Now, however, this one's the easiest one to solve. That's the circular direction, right? And it's subject to these conditions, the periodicity condition, right? So unfortunately, I'll have to erase this. But what I'm trying to say is that if you use the periodicity condition, you see that theta of negative pi should equal to theta of pi, and theta prime of negative pi should equal to theta prime of pi. I'm skipping some steps here because apparently this is the same thing as when you were solving Laplace equation on the disk. Okay, so you remember when you solve the Laplace equation on the disk, you get this. With the Sturm-Liouville equation, theta double prime plus mu theta equal to 0, right? Well, in the circular disk Laplacian, you had lambda here instead of mu. But it's the same story. So what's your conclusion here? Theta has to be? It has to be cosine n theta and sine n theta, right? With C1 or AB, is that the way we like to do? A and B?
Yeah.
Okay. So that's the solution with mu now being n squared, with n from 0, 1, 2, 3. So Is that good? Right, it's the same exact thing as the Laplace one. So that actually tells us something nice. We go back and replace this mu by negative n squared, and then see what we get for this part. So let's write down what we get for. We'll just copy it again and then start slow. Okay. R squared minus R squared kept R double prime R over R of R minus R prime of R over R of R, and then equals to negative n squared. Okay. So what we can do is we can multiply by R of R everywhere. And move everything to the other side, and you get R squared R double prime of R plus R of R prime of R, and then plus lambda R squared minus n squared R of R equal to 0. Okay. Now we are going to yet another change of variables. Usually we use u for change of variables, but that's not convenient for us because we already have u as the original function u. If not, we can use t, but t is already used for time. So unfortunately, we're going to have to use x as square root of lambda r, where this x has nothing to do with the Cartesian coordinates x. Okay, so forget about the fact that r is x is r cosine theta. This has nothing to do with that. It's just some variable that we're just going to use so that this looks a lot easier. Okay. Okay. So if that's the thing that we use, what does that mean? Well, that means let's see. dr, which is this one, right, is equal to dr dx dr, which is dr dx. What's derivative of x with respect to r? Square root of lambda, right? Times square root of lambda. And for the same reason, if you take the second derivative, this is like d dr of r prime. Right? Oh no, but let's see. d dr applied twice, but d dr once is that one, right? dr dx square root of x. And then again use the fact that dx dr dx square root of lambda, there's another square root of lambda. So that tells us that we can rewrite this equation in terms of x as the following. So r squared is r squared, but r double prime as a function of x will now have square root of lambda squared. Okay. Plus r prime as a function of x, if you differentiate r by x, a square root of lambda will appear. Okay. And then plus square root of lambda squared r squared, I'm just writing down lambda squared minus n squared. R of r equals to 0. And then we use the fact that x is square root of lambda times r, right? So what is this same as? X squared, right? What is this? X. What's this? X squared. Oh, and you're considering this as a function of x.
But what do we do with the minus n squared?
Oh, n is n. N is just some number.
I see.
Yeah. N is actually. Yeah.
My bad. Never mind.
Yeah. Okay, so what is that? That's the Bessel's equation, isn't it? Yeah, that's the Bessel's equation for integers. So, for integers, we know that one solution starts with 0, the other solution starts from negative infinity, which is not physical. So, we're going to be solving this one with two conditions. R of 0 should be finite, and R of A should be 0. Right? Because you go it's a radial function, so at the rim it should be 0. We're solving wave equation of the radial, and remember that the condition was that UA theta t is equal to 0 for all theta and t, right? Because when r is equal to a, you're reaching there. Oh, by the way, we have to be careful here because it's this one that's when r is a, it's really that x is square root of lambda. Square root of lambda a is equal to 0. So once you find this, I think it's better to you will have to go back and turn back to R so that you can change this condition. But anyways, okay. Well, we did the hard work already, so let's write down the solution. So what's the solution for R then? It's the Bessel function of order n. And if you insist, we can actually write down the explicit formula for it too, although you don't need it. K goes to 0 to infinity, negative 1 to the kth power, k factorial, k plus n plus 1, factorial, and then it's x over 2 to k plus 2n. So that was the function. But that's it. That's the solution. Okay. And if you want to go back to R, what you have to do is you have to solve for R. R is x over square root of lambda, right? So you have to put that in there, and then you get j of n. So R as a function of R would be jn as x should be replaced by x over square root of lambda. So yeah.
Shouldn't it be replaced by something with R in it?
Yeah, there's no R.
Oh, sorry. Oh, sorry. Yeah, so I got it backwards, sorry. X is square root of lambda r, so it's jn square root of lambda r. Okay. Sorry. Yeah. I mean, of course, if you have a function of r, that should have something with r there. Yeah. Okay. So x is now replaced by this, and that's the solution that we were looking for. All right. So now what can you say? Well, from here, we use the following fact. Jn of square root of lambda r has to satisfy the following fact that Jn square root lambda A has to be 0, right? So, so that actually says, okay. So here's something that I forgot. It can be any constant multiple of this, right? It can be any constant multiple of that. And so that's your R of R. This is R as a function of small r. And we need this to equal to 0. When you plug in A into R, it has to equal to 0. And despite this Bessel function being such a strange function that we've never seen it before we took this class, right? However, you can still manage to say something about this. If two things multiply to 0, either the coefficient is 0 or this is 0, right? Okay. But can this be 0? What goes wrong if this C is 0? It becomes trivial, right? R becomes trivial, and because U is R times theta times T, you end up with a trivial solution. You don't want that, okay? So this should immediately follow that Jn of square root lambda A equals to 0.
Nice.
Now, you have this being 0, and then you have to think about what this means. A is some given thing. This is a fixed thing, okay? So it must be that this gives you a condition for lambda. Okay. So here's what we're going to do. Let J n k be the kth 0 of J n x. Okay. So you recognize this, that Bessel function has lots of zeros, right? There's infinitely many zeros, right? And if that's used, then you can say that the square root of lambda A must be one of these zeros. So that square root of lambda would be J and K over A, and then you square this. This is what you get. Okay. For K 1, 2, 3, and so on, so on. Okay. Now, the Bessel functions start from 0, so I guess we have to be a little careful here. Kth 0 bigger, kth positive 0. Let's kth positive 0. So over here goes like that. This will be Jn1. This one will be Jn2, and so on and so on. Okay. And this is the best we can do because we don't have direct access to Bessel functions. All we can do is just do some numerical computation and see where the 0 is. Unfortunately, that's all we can do. Okay. But knowing that these are discrete values, what does this tell you? This is like what? What is this? Lambda is? These are the eigenvalues. Right? And for each of the eigenvalues, these become the eigenfunctions. All right? Yeah. Okay. So you plug it back in there, and the result is that R must equal to, well, again, because we're just looking for eigenfunctions, you don't need to put the C in. You can just say Jn. Square root of this would be J nk over a r. That's going to be your capital R. Right? And then you go back to the differential equation for t. So what is t double prime equal to? T double prime is negative lambda c squared of t, right? So if you go back, if you move to the other side and you plug that in, you get t double prime plus j n k over a squared c squared t equal to 0. Now if you solve the characteristic equation, you get something times I, so you know that the two functions are sine and cosines, right? So you're going to get t of t equal to c1 times cosine of j and k over a c, c is on top, t plus c2 sine j and k c over a t. Okay. And then you put all of them together, then those are the building blocks. It's kind of crazy, right? So you have this one. Yeah, I didn't want to put a and b there because I already have a and b. So if you think about it, it's really cosine n theta times this one times this one is 1. Okay, and you can have cosine times sine times this one. You can also have sine times cosine times this one, and yeah, like 4 different terms. However, instead of, I mean, we can continue this and write down the solution, but that will be actually less of our concern. What we'll be more interested in will be the following. Look at what these are. These are periodic functions in time, right? So what do you call this coefficient when you have a function of time? It's called the angular frequency. Right? So there's a formula for angular frequency that you have omega equals to 2 pi f, where f is the frequency. So if you take this value and divide it by 2 pi, that's the frequency of this thing. So what it means is that at least for that specific value of radial function combined with something like this, if you fix an n and a k, it's going to be a mode of vibration that has a certain pitch, because frequency means pitch. Right? So you can start by looking at these starting from the very first one, like J0001, 11, 21, and so on, and you can look for their ratios between the frequency pitches, and that's going to tell you all these different frequencies that's generated when you beat a drum. Okay? And from that, you can actually think about how a drum should sound like. Okay, so that's going to be a topic for next week.